Hi everyone. Welcome to the online seminar on the mathematical foundations of data science. Thanks for joining today. Our seminar is generously sponsored by 2 Sigma. It's my real pleasure to introduce our prestigious speaker, John Asher. John Asher is an applied mathematician, and he is currently a 4th-year PhD student at the math department in MIT. Prior to MIT, he received his bachelor's degrees and master's degree in mathematics from Penn State University. He has also been a professional football player from the year 2014 to the year 2017, playing for Baltimore Ravens. He has won many awards in both academic and athletic careers. For academic achievements, he is a Dean of Science Fellow in MIT. He was named to a Forbes 30 under 30 list of outstanding young scientists. In Penn State, he was named Student Marshal and was a recipient of a Comet Anderson Award and the Evan Johnson Memorial Scholarship. As a football player, he was a recipient of James Sullivan Award, a William Campbell Trophy, and Senior Class Award. His research interests lie broadly in the fields such as numerical analysis, graph theory, and data science, machine learning. And he has published many great papers in these fields. By the way, his autobiography, Mind and Matter, A Life in Math and Football, is a New York Times bestseller. The title of his talk today is Stress Minimization for Low Diameter Graphs. Please join me in welcoming him.
Oh, wow, that was a very strong introduction. Thank you. Yes, so today what I'd like to talk about is looking at embedding graphs into Euclidean space and attempting to minimize some sort of energy or stress function. This research very much lies at the intersection between more traditional sort of graph drawing techniques and topics and things that are quite relevant and important for machine learning and data science. This is why I thought it would be a reasonable topic for this seminar series. I should say that from this talk, you might get slightly a sort of wrong impression about me. I would say that my thesis work at MIT and the sort of majority of my research does lie largely in sort of numerical linear algebra, topics in graph theory, and sometimes how these things apply to problems in data science and machine learning. And so this is the perspective I often take. This is joint work with Fred Kohler, who is a PhD student at MIT as well, who focuses in machine learning. Okay. So first, I want to just take a couple minutes to talk about what are we going to go over, the steps we're going to take, and sort of what we are hoping to sort of gain by the end of this talk. So first off, we're going to introduce the concept of stress minimization. I'm going to show you guys some basic results. I want to survey some of the popular heuristics that are out there for solving this problem, for sort of approximately minimizing this objective function. I want to take a look at some new algorithmic lower bounds for this problem, which in my opinion are sort of quite nice and elegant in some sense. And I will sketch a reduction showing that minimizing stress is actually hard, NP hard to be exact. We'll take a look at an efficient polynomial time approximation scheme for this problem. And this efficient polynomial time approximation scheme is going to be a sort of combination of some recent results for approximately solving dense CSPs paired with some fairly natural discretization arguments and like an epsilon net argument paired with some sort of Lipschitz bounds. And then after that, we're going to examine some experimental results that show that the proposed PTOS, that's short for polynomial time approximation scheme, is actually somewhat natural in a sense, improves the experimental results you see, and gives some sort of inkling as to sort of what people should perhaps look at next in this area, in this regime. And you'll see what I mean as we progress further. So let's start with the first part. So first we have to introduce what we're talking about. So the stress minimization problem. Imagine we're given n objects. We'll just order them, let's say 1 through n. Some distance matrix where, okay, I list a couple sort of nice properties, but in general, I want you to think of this as a metric. So in addition to the properties listed, I would like triangle inequality. That would be nice. And some dimension d. What we want to do is we want to embed these n objects into RD such that we minimize this so-called stress function. Sometimes it's called an energy function. In other places, it's called the Kawhi objective function, which will become obvious for some reasons. But this energy function is given by the sum over all pairs, where we square the difference between the distance of these 2 points being embedded in RD and their sort of abstract distance given from our distance matrix. And the cost that we incur for sort of the error in each of these edges is weighted by some just weight, Wij. In practice, you should think of the dimension d that we're embedding in as quite small. Usually d is 2. And one very common choice of weight is just taking the weight between two objects ij to just be 1 over their distance squared. And this is most popular because it's been shown in a number of ways, including experimentally, that this somehow gives you the nicest looking drawings, although this is obviously somewhat subjective. This objective function actually has a sort of a more physical interpretation, a force-based interpretation. You can think of this instead of as objects with some metric, let's just focus on the case where we have some graph, let's say. So we have an unweighted graph with n vertices and some edges, and we want to embed this graph into RD. And we want to minimize the subjective function. You can imagine that this corresponds to a very natural physical situation where the locations of these vertices are like particles. And for each pair of particles, they're connected by some sort of spring. And the equilibrium length that you want is their graph distance. So when you embed them in RD, you would like vertex I and vertex j to be the exact distance that they are in the graph. But you can't necessarily have all pairs of vertices at the exact distance that they would be in the graph. And so you sort of incur a potential function that is related to this spring with a spring constant of 1 over their distance squared. So the idea being that vertices which are closer together in the graph, their spring is in some sense stronger. These really want to be at the correct distance, whereas vertices that are far apart, yes, they do have a spring between them, but this is a sort of much weaker spring constant. And you'll see that this sort of affects the layout much less. Okay. I should say that this stress minimization problem is just a specific example of actually a wide range of so-called force-based techniques for embedding graphs. This field is actually, very sort of diverse in different techniques. In my opinion, I would say that this field really traces back to the work of mathematician Tut, who came up with a very, very beautiful result, which states that if you have a 3 connected planar graph, and suppose you pick some face of this graph, you embed this face in the plane such that its vertices form a convex polygon, and you embed every other vertex at the mass center of its neighbors. Tut was able to prove that this embedding is always planar. And in fact, this embedding has a number of other nice properties. If this sounds interesting to you, I encourage you to go to my website. I actually have a recent preprint on this subject, which I think is quite interesting. But since Tut's work in the 60s, there's been a lot of different techniques, And I will say that from the machine learning community, there's been a great renewed interest in force-directed layouts, particularly this very popular technique, this algorithm T-SNE and UMAP, which is used to sort of visualize high-dimensional data. This is actually what sort of led to this line of research. My friend and office mate, Fred Kohler, he's a sort of machine learning enthusiast. And so when he sort of thought more and more about these recently popular algorithms, at their core, they have a sort of force-directed layout. And while they use more complicated objectives, the main concept is the same. And so this work is really inspired by trying to understand these type of objectives, especially these objectives which are sort of highly non-convex, and understanding what you can do with them. Okay. So what can we say about these things? I think it's pretty important that we go over what is known and sort of what we don't know and what we sort of hope to understand. So first of all, I should mention that all of these techniques that I've talked about, T-SNE, UMAP, all of these things work very well in practice. But all of these techniques involve optimizing some non-convex objective without a given guarantee of success using, a so-called heuristic. There has been some rigorous analysis. For instance, T-SNE has been analyzed under certain conditions, and it's been seen that, for instance, T-SNE sort of gives you sort of the structure you want when you, let's say, look at well-separated clusters. But more general, stronger guarantees for algorithms like T-SNE and UMAP sort of don't seem to exist at the moment. And I think this relates in part to their sort of complicated objective functions, which are, okay, perhaps not the most complicated, but I would say more complicated than this stress minimization formulation. Okay. And so for this reason today, and sort of in this sort of work, we're focusing on this simplified stress objective that's based on these idealized springs, excuse me. It's worth noting that experimentally, it's been observed that for this problem in particular, it's relatively easy to find high quality minima, despite the fact that this is sort of a highly non-convex problem. But to our knowledge so far, there hasn't really been a mathematical explanation for why this is the case. Okay. So next, I want to survey some of the most popular heuristics for approximately solving the stress minimization problem. One of these techniques, called the Kawhi algorithm, this technique was created specifically for unweighted graphs and dimension 2. And this heuristic is fairly straightforward. What they do is they just perform an alternating minimization on different vertices by choosing the next vertex by seeing the one that maximizes the sum of squared partial derivatives in the two different components. For each vertex, they just perform minimization by Newton's method. So this is a sort of very popular technique, and you will find this heuristic in a lot of graph drawing software. For instance, GraphViz has this algorithm. It's quite popular. Another popular heuristic, which comes more from the stress majorization and multidimensional scaling community, is the so-called Smokoff algorithm. And the idea behind this algorithm is also fairly natural. If you think about our stress function, our stress objective, if you expand this out, so for instance, go back to our stress objective, if you expand this out, you'll really come to sort of understand where the difficulty in this minimization problem comes from. So when you expand this square, you'll see that we do get a quadratic term, which is very easy to deal with. We get a constant, not even a worry. But then we get this third term, which really gives us some trouble. And so the idea of this Smokoff algorithm is to take this second term, which is really the thing that makes optimization tricky and difficult, and try to just upper bound this quantity, or in this case, because it's negative, lower bound, we're trying to come up with some quadratic function that is always greater than our stress function, and yet the minima of both are the same. And so the main idea of this algorithm is to just perform alternating minimization on the components of this quadratic function. And this has actually been shown that it monotonically decreases stress at each iteration. So this is another popular heuristic, but note that this guarantees you'll move towards a local minimum, but not necessarily a global one. And these have been two very popular algorithms for solving this problem. I should mention that the Smokoff algorithm is more general in the sense that this was created for a more general weight function and not just graphs, but general data. But there's another heuristic, just stochastic gradient descent. This is very natural and obviously very popular in a lot of contexts. And it turns out that stochastic gradient descent for this objective function in particular actually performs slightly better than Commodore Kawhi or the Smokoff heuristic. And this is sort of an interesting phenomena. And for this reason, when we get to experiments, I want to say that you won't see experimental results for Commodore Kawhi or Smokoff because, well, some of this work has already been done and we'll focus on stochastic gradient descent. Okay. And this is sort of what we'll compare to. And in some way, some of the analysis of this talk will attempt to sort of help us understand why stochastic gradient descent might be performing quite well in practice. So this brings us to the third part of this talk. Let's look at this stress function and try to come up with some algorithmic lower bounds to understand what we can and cannot say in terms of algorithms. So, this is an objective function that's been around for a while. There's a number of very popular heuristics, and it seems reasonably likely that minimizing a stress function might be, computationally hard. And it turns out that this is the case. And if you'll allow me, I'd like to sketch for you what I believe is actually quite a nice hardness reduction. And this is, well, I will sketch a sort of simplified version. And I think this has some nice elegance to it. It's something I like. So first, I want to note that I'm not going to prove a reduction for just the sort of stress function for the specific case of an unweighted graph and this weight of 1 over the distance squared. But I want to show you a reduction for a slightly more general and simpler case, simply because the analysis here will be sort of much better and it's much more, it's much more natural for a talk like this. You don't want to see anything ugly. You want to see something sort of clean. And so for algorithmic lower bounds, we'll focus on minimizing a weighted stress objective where our weight, Wij, is now parameterized by some W of vertex U, W of vertex V, and again, it's divided by the distance between vertices U and V squared in the graph. Okay, so we want to sort of minimize this weighted stress objective over all functions Y, which map our vertex set into R. This is equivalent to embedding our graph into 1D, the real line, for some fixed graph and some choice of weights. And we'll say that these weights need to be natural numbers. If these weights are natural numbers, you can actually think of minimizing the stress function as having some data and you have more than one copy of certain data points. Like your choice of weight, let's say WU, means how many times does vertex U show up, let's say, in your data set, perhaps. So this, while being slightly more general than the objective function I showed you previously, is a very natural one. And so we'll sketch an algorithmic lower bound for this, and I'll just briefly talk about how you can get higher dimensional versions and unweighted versions. Okay. So what we're going to do is we're going to sketch a proof that this weighted stress minimization is NP hard. And what we want to use to do this is actually a reduction from something called max all equal 3 sat. And so first off, I want to say that I don't want to assume that everyone sort of viewing this talk is very familiar with sort of satisfiability. And so I want to really sort of slowly go through what is max all equal 3 sat, and then sort of show you what I think is sort of a pretty reduction, in my opinion. And the decision problem we're going to look at is you have a graph, you have a weight function, you have some constant L, and you need to decide if you can embed this graph into the real line such that its energy is less than or equal L. You need to decide whether you can do this or not. Okay. So let's go over max all equal 3 sat. So for this problem, you're given n variables, x1 to xn. These can either be set to true or false. These n variables correspond to 2n literals. So a literal is just a variable. It can be negated or not negated. So if you have n variables, this means you have 2n literals. So let's say x1 is set to true. Then this x1 bar is the negation, which means x1 bar is set to false. Okay. We're given m clauses, C1 to Cm. Each of these consists of exactly 3 literals. So you can imagine we have this set of literals, and then we have m different subsets, each of order 3. And for our specific sort of reduction, we do require that literals do not be repeated. And for now, I'm just not going to go over sort of how you show that version of max all equal 3 sat is hard, but we will take that for granted. The max all equal 3 sat problem attempts to find some assignment of these variables, x1 to xn, either as true or false or 0, 1, that maximizes the number of these clauses, or you can think of them as sort of subsets of the literals of order 3 that have all of their literals equal. So either their 3 literals are all 1s, so 1, 1, 1, or perhaps they're all 0s, 0, 0, 0. Now, it's worth noting just for a sanity check that if I remove the max from this sort of problem, you can see how this is quite an easy problem to solve, because for, let's say, all equal 3 sat, we can tell that for this to be satisfiable, we can look at every single clause, and we know that all of the literals in each clause have to be equal. And so this is obviously polynomial time, but the max version is much more complex, and luckily for us, this is hard. So now we can continue with a reduction. First, I want to show a fairly simple example to make sure sort of we understand this satisfaction problem. So suppose we just have 3 variables, x1, x2, x3, 4 clauses, C1, C2, C3, and C4, like I've shown you. You should note that if we just set x1, x2, and x4 to equal 1, x3 to equal 0, we can note that C1 has all literals equal to 1, I believe. C2 has all literals equal to 0, and C3 and C4 have some mix. And you can actually show that satisfying 2 out of the 4 clauses is the best you can do, because we see C1 and C3 can't both be all equal at the same time, because C1 has x2 and x3 bar, and C3 has x2 bar and x3 bar. So we come across an issue there, and a similar issue holds for C2 and C4. And so you can see that satisfying 2 clauses is the best we can do, and it's done by this assignment of the variables. Okay, so now let's move on to our reduction. I'm just going to sketch this for you. So suppose we have some instance of max all equal 3 sat, where we have some literals L and clauses C. And let's use these guys to build a graph. What we're going to do is first we're going to include one vertex. I'll just call it V, V0, V naught. And then I'll add a vertex for every literal, and I'll add a vertex for every clause. And how do I want this graph to be connected? Well, I want all my literals to be connected to this, this vertex V naught, which I'll call my anchor vertex. And you can even suppose it sits right at the origin. So I want all my literals to be distance 1 from this sort of central vertex. I want all my clauses to be attached to the literals they contain. So all the clauses are at distance 2 from this anchor vertex. And I want all the literals that are not negations of each other to be connected. And I want to weight these so that my V naught, this anchor vertex, is very, very heavy. It carries some significant weight. My clause vertices are much less heavy, but still have some significant weight. Sorry, my literal vertices are much less heavy, but still have some significant weight. And then my clause vertices still have some weight, but are much less heavy than, let's say, the literals or this quite large anchor. Okay, and where n is sort of very large with respect to the number of variables and with respect to the number of clauses. And just imagine n is quite large. And so what can we sort of say about an optimal embedding of this graph? What does it have to look like? Well, the first thing you'll notice is that we can just assume that this large vertex sits at 0 on the real line. And the weight is so large that, in fact, all the other vertices very much prefer to be almost exactly the correct distance from it. And so for our purposes, let's just assume that they have to be exactly the correct distance. You can sort of analyze that this nearly has to be the case. And so roughly speaking, your literals either have to lie at +1 or -1, and your clauses have to lie at +2 or -2, because the clauses are at distance 2 from this anchor vertex, V0. Now, variables and their negations are at graph distance 2, and all other literals are at graph distance 1. And so when you partition literals between +1 and -1, they split 50-50. You have n at +1 and n at -1. And negations prefer to be on opposite sides. Clauses are at distance 1 from their literals and distance 2 from others. And so every clause vertex prefers to be on the side of the graph corresponding with a majority of its literals. Now, you can sort of already see naturally that choosing whether a variable or a negation lies at 1 or -1, this corresponds to an assignment, a truth assignment of the variables. For instance, you can take all the variables, or rather all the literals lying at +1, and you can simply say all of these literals are true. And what you'll notice is because the clauses always prefer to be on the side with the majority of its literals, you'll note that the energy of this embedding actually depends heavily on how many clauses are on the side with all 3 of its literals. Namely, how many clauses are at the exact distance it should be from all of its literals. And so this gives us an algorithmic lower bound for a version of stress minimization. This reduction shows that this is hard, and in fact, this is strongly hard because you'll note that sort of the inputs, all of these are like all of the sort of things which we have constructed are sort of polynomial in the input. So because this n is this large n is a polynomial in little n and m. Okay, so we know that this problem is hard. Now let's try to take a look at how we can approximately solve this problem. And what we're going to make use of here is some fairly recent and sort of strong results regarding sort of greedy CSP algorithms, greedy constraint satisfaction problem algorithms. And before we do this, what we require is some sort of guarantee about if we have some graph, we'd like to be able to know roughly how big is its embedding. This is something that's quite useful anytime you need to sort of approximately minimize something, or you want to discretize some problem. You really want to be able to say how big does my grid have to be. And so what I'll show you guys is a fairly slick upper bound on how sort of what the diameter, let's say, of an embedding of a graph is bounded by. You should note that better bounds can come through more complicated arguments, but I think it's often best for, for presentations to show maybe worse bounds with simpler arguments. So suppose we have a graph G with diameter capital D. Please excuse the abusive notation. And using a simple argument, we can actually show that there exists an optimal embedding of x1 to xn into any dimension little d, such that all of these points lie fully in the ball of radius d squared plus d. Okay, and so this gives us some sort of bound on how big our embedding is going to be based off how large the diameter of the graph is. I mean, the title of the talk is sort of these embeddings for low diameter graphs, and we really haven't touched on the diameter part of this, although you should note that the hardness we just showed is specifically for graphs of constant diameter, because these are the sort of graphs we're looking at. And so this is relevant given that this algorithm we're about to come up with really performs well for low diameter graphs. Okay. And so how are we going to show this? Well, the sort of simplest thing you can do is just look at first order conditions. And so let's suppose we have some optimal embedding of our graph in RD. Without loss of generality, let's suppose that the largest distance between any 2 points in our embedding occurs between 2 points sort of on the x1, well, I shouldn't use x1, on the sort of E1 axis. So, where E1 is the first vector in our standard basis. Let's order these vertices, the embedding of these vertices, such that they go from smallest to largest with respect to their first coordinate. And without loss of generality, let's suppose that the middle sort of point or middle vertex, when we order our vertices in this way, embeds exactly at first coordinate 0. And we can do this simply by shifting. So we can set our x1 to be negative alpha times E1, our standard basis function. And for our purposes, let's assume that alpha is further out than the diameter. If we just differentiate our stress function with respect to the first coordinate of this first point, we sort of obtain this, this somewhat nasty but not too bad equation. And what we're going to do is we're going to note that this sums over all of our n-1 other points. But by assumption, we know that half of the points lie on the other side of the first standard basis function. So this means we know that n over 2 of these points are further than d away from our first vertex, which means that their spring is stretched too far. And so to have this equality, we know that these remaining n-1 over 2 vertices on our side have to, their springs have to be somehow a little bit too tight, and this has to balance out. And so what we have, and you don't need to worry about the math too much, and we have lost a little bit of bottom slide. Let me fix this. Give me a second. We have lost a little bit of the bottom of the slide, but all you can do is you can simply lower bound the sort of contribution from vertices which are too far away, upper bound the contribution from vertices which are quite close, and by simply showing that you need to have the correct inequality here for us to have sort of equilibrium locally, we get that the maximum distance that this point can be away is d plus d squared. And so now we have, for some given graph G with, let's say, diameter d, now we have a provable guarantee that the optimal embedding has to sort of lie within a ball of radius roughly like the diameter squared. And so the next thing we want to do is try to make use of, of a greedy algorithm for, let's say, a max constraint satisfaction problem. So for instance, let's look at a very simple greedy approach. And we're using this approach specifically because what's most important for our setting is that we have some algorithm that really has the mildest dependence on the size of the alphabet. And so let's consider the following greedy algorithm, which is quite simple to state. We're going to sort of randomly shuffle our variables. And what we're going to do is we're going to look at every single possible assignment of, let's say, our first 1 to t naught variables, where each of our variables can equal sort of any quantity in our alphabet. And we have these sort of sum of functions which we're attempting to maximize. And the main idea of this max constraint satisfaction problem algorithm is that we take these first t naught and we actually try every single possible embedding for these variables. And then for the others, we simply sort of place them greedily. And then what we do is we return the output over all those different choices, which maximizes our objective value. And we are dealing with a minimization problem, so you should think about this sort of technique. It's sort of the same, except imagine, these Fij, these sum of sort of functions. These are just, we set them to be negative, and then we have a minimization problem. And so for this algorithm, there's actually a very simple and nice guarantee, which is, suppose we have some alphabet and we have some function for every ij that maps from this alphabet squared to some bounded interval. Then we can show that for any epsilon, this greedy algorithm, by taking our number of points, which we're going to sort of brute force search over to be 1 over epsilon squared, this runs in time, which is polynomial with respect to n, and it returns some output such that in expectation, sort of our outputted, let's say, approximate solution only differs from the optimum by epsilon times m times n squared. And this expectation is naturally over the randomness of the algorithm. Okay. So just note that this algorithm is doing something. It's doing something, pretty strong, because if you wanted to sort of brute force compute the maximizer, this would be sort of in time like the order of the alphabet to the power n. So this is like exponentially slower. Our guarantee is an expectation, but okay, for machine learning people, I just wanted to state, in case we had some people who are sort of unfamiliar with these typical tricks, you can always convert this to a high probability guarantee. You just repeat the algorithm, apply Markov's inequality. That's fairly straightforward. There do exist deterministic algorithms that have similar guarantees, but these things, in my opinion, are much, much more complicated to describe and not as easy to implement in practice. And so this is why we sort of chose this specific greedy algorithm. And of course, we're solving a minimization problem. We're attempting to minimize stress, which is the same as our maximization problem. We're just minimizing these Fij. Okay. So we have this problem to sort of solve some sort of discrete optimization problem. So the next ingredient we need is some sort of guarantee that our continuous optimization problem and a sort of related discrete optimization problem are not too far apart. And so the natural thing to do here is to make use of epsilon nets and sort of, bound our functions using, some Lipschitz constants. So first of all, you should note that we can show that our stress function is the sum of Lipschitz functions, where these are Lipschitz with a constant that depends on sort of the diameter of the embedding, which we showed was just the square of the diameter of the graph. And from this, you can just use a sort of typical epsilon net argument that you can find in sort of a lot of standard places. And when you add these two things together, you just get a very simple and nice guarantee that, okay, by constructing an epsilon net in this ball that we know our sort of optimal solution lies in, we can get a approximate discrete problem that is very close in terms of its optimum to our continuous problem. And for anyone sort of somewhat unfamiliar with the concept of an epsilon net, let's just suppose we have some ball of some radius. And this is just stating that for any sort of choice of epsilon, there exists some subset of this ball where the number of points, in this case, for this guarantee, is at most 3r divided by epsilon to the power d, such that any sort of point in our ball is at distance at most epsilon from some point in our set. So this is the concept of an epsilon net. And yeah, there are many places you can sort of read more about these things. And so just combining our Lipschitz bounds with a sort of simple epsilon net, we get a nice guarantee about sort of a discretization of our problem. So suppose we have some embedding of our endpoints such that they're all within a ball of radius r. And let's produce some epsilon net. Then we know there exists some embedding where our embedding is exactly at points in our epsilon net such that their difference in energy is at most like 4 epsilon times r times n squared. Okay, and this just simply comes from a Lipschitz bound for each of the terms in our sum. Okay. And so from this, we can actually build what I feel is a fairly natural sort of efficient polynomial time approximation scheme. And I say efficient because, as you will see, this is polynomial in n for sort of any choice of our epsilon, but this is not a fully polynomial time approximation scheme because it is not polynomial in our epsilon. Okay, so the simple algorithm is just this. Let's build an epsilon net for our ball, apply this greedy CSP algorithm, and simply just return what we get. Okay. And you can prove a fairly straightforward theorem about this. This produces some algorithm that runs in time n squared times something that depends on r and epsilon, and outputs some approximate solution that's within epsilon times n squared of the optimum solution. Okay? And again, this expectation is over the randomness of our algorithm. And the proof is fairly straightforward. We just sort of choose our epsilons from both of these arguments in a good way, and we get this nice theoretical guarantee. I should mention that you can actually get a sort of runtime which can be improved to sort of n squared plus a term that depends on our big R and epsilon, where big R you should think as like diameter. But it's a slightly more complex algorithm, and I feel that the one we're using is sort of simpler to explain and sort of simpler in practice. And of course, these expectation can be converted to high probability just by repeating the algorithm, which is fairly natural. And so now I want to look at briefly a couple experimental results with my my last few minutes and come to understand that this approximation algorithm, which we just described, actually does improve the sort of embeddings you get in practice for very small choices of T naught, where T naught is the number of vertices which we're sort of brute forcing over. So for instance, I'll just show you a couple graphs. So this is a embedding of a Watt-Strogatz graph. And here I've included 4 different plots. So in the top left, this is simply just our greedy algorithm, where here our greedy algorithm with T naught equals 3. So we're only brute forcing over 3 vertices. Gradient descent is in the bottom left, stochastic gradient descent. And in the top right is a sort of combination of the two, starting with this greedy technique and then using gradient descent. And in the bottom right, I simply included a Laplacian embedding just because, well, sort of these Laplacian embeddings are sort of quite natural for many settings to sort of understand what a graph looks like and also to try to get quality embeddings. And I do want to show you that sort of this objective function we're minimizing is really doing something different and more complex than your typical, let's say, Laplacian problem, which you can imagine that the complexity of our embeddings and sort of the quality of our embeddings comes from this sort of extra term that I was talking about previously, which simultaneously makes our objective function sort of non-convex and makes it hard, computationally hard, makes it sort of tough to globally minimize in practice. But this is also the thing that gives it a sort of much deeper flavor than your typical Laplacian embedding, because without this term, obviously sort of the things that minimize stress are closely related to sort of the graph Laplacian. Okay. And what we see through sort of a large number of experiments is that gradient descent performs well. Our greedy algorithm, even for very small choices of brute force search, actually as a initialization for gradient descent, is a sort of very good initial choice and performs quite well. Here's another sort of embedding of a typical graph. And here's a embedding of a 3-community stochastic block model. The colors correspond to the latent community assignments. And you can see that this sort of greedy technique, this is also just for 3 vertices, this greedy technique over a very small number of vertices, followed by gradient descent, actually performs quite well in practice. And so this sort of leads us to ask some more theoretical questions about sort of why does stochastic gradient descent seem to perform well? And it should be noted that this sort of greedy technique that we've sort of come up with can be thought as sort of a more rigorous version of stochastic gradient descent, actually. You can imagine what we're doing is we're sort of brute force searching over some number of vertices, and so we're sort of testing a lot of different initializations, and then we're sort of greedily minimizing everything else. And so the algorithm that we came up with that has this approximation guarantee already has a very sort of stochastic gradient descent flavor. And the sort of natural question that starts to sort of come out of this is, does gradient descent itself, with, let's say, enough random restarts, also have a similar guarantee to our approximation algorithm? And I would guess the answer is most likely yes, although this might be somewhat complicated to analyze in practice, because these gradient-based optimizations seem to find high quality, although they're not global minima. They seem to find high quality minima, even though this loss is sort of highly non-convex. One thing to note is that if we combine sort of the analysis of this talk and of our work in general with, let's say, a different sort of CSP theorem, then you should note that you can run a variant of this sort of greedy algorithm, which I showed you, without the initial brute force step and achieve an additive sort of epsilon n squared approximation, but the dependence on epsilon is much, much worse. And so this other sort of version of greedy CSP, which I'm describing, sort of feels even closer to gradient descent. Gradient descent itself is sort of a greedy procedure, and it seems quite likely that although maybe sort of a guarantee with dependence on epsilon like the first greedy CSP I showed you may not be possible, it seems quite plausible that in fact just stochastic gradient descent may have such a strong guarantee for, let's say 2 to the power 2, 1 over epsilon squared initializations. And so this is sort of a interesting possible sort of future thing to look at that I think is quite possibly true. And in addition, I think that this sort of analysis may help us sort of in the future understand some of these more complicated force-based sort of layout techniques like t-SNE, like UMAP, to sort of understand why these heuristics work so well, and to perhaps gain sort of more theoretical footing for these sort of very commonly used techniques. So that is the end of my talk. I wanted to say thank you for having me, and if you have any further questions, feel free to shoot me an email. This work that I talked about, I'll sort of reiterate what I said at the beginning. This is joint with Fred Kohler. This is in preparation. You should see a preprint on arXiv sort of within the month. And I encourage you, if you sort of enjoyed this talk, in particular some of the graph perspectives of this, feel free to take a look at my other work, which is sort of heavily sort of focused on sort of embedding graphs and sort of spectral graph theory related to certain optimization problems, and some of my work in sort of numerical linear algebra in general, which sort of that work more sort of forms the sort of basis of my thesis. And so I'd like to say thank you for having me, and feel free to let me know what questions you may have.
All right. Thank you, John, for the very nice talk. So maybe let's go over some of the questions. The first question is regarding the algorithm. I was wondering whether it is possible to let the algorithm be adaptive to the number of vertices of the graph. For example, can we make it online? That is, when the new data comes, we can grow a bigger graph or embed a bigger graph.
Oh, I see. That is a very good question. Let me think. So I think for approximation guarantees, without any sort of assumption, you would most likely not be able to sort of piggyback, but suppose you have an assumption of the form that sort of this data is coming from some sort of distribution, then you can, I'm going to say that it seems very, very likely that you can actually get provable guarantees that the brute force that you've already done, simply taking your optimum and just locally sort of locally optimizing from there, most likely gives you provable guarantees. And in fact, for heuristics, this is certainly the case.
Okay, thank you. And maybe following up the first question, I was wondering, in terms of doing embedding, is it possible to incorporate some prior information we know about the data into the embedding algorithm?
Yes. So in fact, for sort of more complex, and I can go back to the beginning to talk about this. In fact, for sort of more complex data settings, you can actually, although, okay, they typically choose this weight to be sort of scaled by sort of distance squared, which is extremely natural and seems to work very well. You can sort of tweak this, and you can sort of take this and sort of multiply each sort of term by some sort of confidence you have. So for instance, if your data comes from somewhere where you have some level of confidence with respect to each point, you can, with respect to sort of the error in, what's the word? In your actual observation, you can incorporate this into your weights so that certain weights get sort of valued more sort of heavily than others, the ones that you're more confident about. And so these are sort of ways in which sort of the data that, the sort of prior information that you have with respect to which weights are very important, which weights do I know, and which weights am I less sure about, this can be represented in your sort of embedding. And also if you perhaps know a priori that my embedding needs to satisfy a certain structure. Like for instance, you know for some reason in your application that the embedding of your data or the embedding of your network needs to be such that a certain subpart of this network needs to be embedded in a very particular way. You can force this to be the case through the weights you choose for those by setting those to be sort of scaled quite large compared to others. It forces this sort of structure which you want, and then places all the others sort of at the minimizing place, given this sort of extra information that you know. So yes, there's a number of ways to sort of do this.
Mm-hmm. Okay, thank you. So briefly speaking, you can incorporate the prior information into the design of the weights.
Yes.
Okay, thank you.
Yeah.
And maybe the last question is regarding some empiricals, the empirical aspects of embedding. So from a practitioner's perspective, if I run an embedding algorithm on the data set, so how can I know that the result is meaningful or the embedding is good? Just by, is there a criteria or a loss function that I can compute numerically that can tell me whether the embedding results is meaningful or not?
Yes. So while there's not as much work on this as I would like to see in this literature in particular, I would say that, I mean, obviously this is something that's quite well studied. I mean, let's talk specifically, let's suppose you have some data and it has some inherent structure. By embedding this in different dimensions, different low dimensions, and observing the stress function in each dimension and how it scales, you can gain information in some sense about what is the natural low dimensional embedding of your data. And while I'm not an expert on this, I do know a little bit about this, and I would say that this is not unlike sort of typical sort of procedures for this sort of thing in other sort of areas of like unsupervised learning. But I feel that for this in particular, there's a real lack of sort of research on that particular topic as opposed to other areas. And I would say that also a lot of these techniques focus specifically on d equals 2 because they want to output something that you can see and ideally tell you something visually. And so I would say choosing your dimension in terms of understanding what dimension perhaps your data mostly lies in some sense. This is sort of a topic that hasn't been hit on as much, but there are sort of natural techniques you can use. But I would say that in general, a lot of these techniques really focus on embedding in 2D so that you can visually see something about your data.
Mm-hmm. Okay, thank you. So that's basically all the questions that I have. Thank you again for the very nice talk. It's our pleasure.
No, absolutely. Thank you for having me.
Yeah, thank you.
Thank you. And also thanks everyone for joining. We are looking forward to seeing you guys next week.